Okay, so let's talk about some of the rules that govern t-distributions. So the first one you already know. As t-distributions get more normal as n gets bigger. And this makes sense if we step back and think about it for a second. Imagine if n equals n, right? If n equals n, then what would your s be, right? If n equals n, if your sample is like the entire population, then s, right, should be much, 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 much closer to the actual population standard deviation, right? So much better than when n is small, right? It's still a little off because the n minus 1 thing, but it's very, very close, right? And that's the closest you could get. And so t-distributions are more normal as n gets bigger because s is a better estimate of sigma as n gets bigger, right? And that makes sense, right? The problem all stems from s. It's variability, right? But as s gets better and better and better and less variable and more accurate to the population, then t gets better, right? Because t is based on s, right? So that's why t-distributions are more normal as n gets bigger. Now, t-distributions are really a family of distributions. It's not just one distribution. It's a whole bunch of them that are alike in some way. And it depends on n. Rather, it depends technically on degrees of freedom. But you could say it depends on n sometimes because degrees of freedom is often n minus 1. Now, there will be other kinds of degrees of freedom. This is the one you need to know for now. But later on, we will distinguish between different kinds of degrees of freedom. That's why degrees of freedom is actually important as a general idea. It's just the number of data points minus 1. So we have a family of distributions. They all look sort of alike, right? They're all symmetrical, and they're unimodal, and they have that sort of, bell-like shape, but they're not quite normal. Not all of them, at least. And as n gets bigger, or as degrees of freedom gets bigger, the distribution becomes more and more normal. Okay, so let's step back and talk a little bit about degrees of freedom first. So let's assume there are 3 subjects in one sample, right? So 3 subjects, so n equals 3, right? That's what I have right here. And we know that just by the blind formula, n minus 1 degrees of freedom is 2, right? But what does this mean? Well, here's the thing. Let's assume there are 3 subjects in one sample, and let's say it's some score on a statistics test. And so they could score from 0 to 100. And if I said, oh, pick any 3 scores you want, and that could be those subject scores, right? Then your degrees of freedom would be 3. You are free to choose any 3 scores. You're not limited, right? You're not restricted in any way. But if you figure out any sample statistic, let's say the mean or the variance, right? So if you figure out any sample statistic, then if you randomly picked 2 of those scores, you can no longer just pick the 3rd score freely. You have to pick a particular score because you already used up some of your calculations for the mean, right? So the mean will constrain which 2 scores you could pick. And this logic will become more important later. So let's put some numbers in here, okay? So let's talk about the case when n equals 3 and degrees of freedom equals 3, right? So it'll be like there are 3 subjects, and they could score from 0 to 100. So pick 3 scores, right? I'm totally free. I could pick, 87, 52, right? My last score, I could pick any score I want. I could pick 52 again. I could pick 100. I could pick 0, right? Doesn't matter, right? So I could just pick any score I want. And if I erase one of these other scores, I just put in a different score, right? And it doesn't matter. I'm very free to vary. But let's talk about this, most situations that we have in statistics where we figure out summary statistics. So here we have n equals 3, but degrees of freedom now equal 2. Here's why. The score is the same. Score can go from 0 to 100. But we also found the x-bar, right? We found the x-bar to equal 50, let's say. If we found that the x-bar equals 50, then we can't just pick any score all 3 times. Can we pick any score for the first one? Yeah, I could pick 0, right? Can I pick any score for the second one? Sure, I could pick 100, right? But now that third score, I can't pick any score. If I picked 72, my mean wouldn't be 50, right? If I picked 42, my mean wouldn't be 50. If I picked another 0, my mean wouldn't be 50. That's a problem, right? And because of that, if this is my data set so far, I've been free to vary so far. I freely chose this guy. I freely chose this guy. But this last one, I am locked in. I have to choose 50. That is the only way I could get a mean of 50. And that's what we call degrees of freedom. This logic is going to become more important later on. But for now, what you could think about is because we're deriving other summary statistics from our sample, we're not completely free to vary. We've sort of locked ourselves down. We've pinned ourselves down and sort of built little gates for us at the borders, right? Okay, so now you know degrees of freedom. And we know that as degrees of freedom, or n, goes up, we see more and more normal-like distributions. So I've drawn 3 distributions here for you. And here, you might notice that I've used basically the same picture of a curve for all 3 of these. And so you might think, oh, they have all the same distribution. Ah, not true, because you have to take a look at the way that I've shown you the t down here, right? The way that I've labeled this x-axis, or t-axis in this case, is really going to change our interpretation of these curves. Now, remember what the normal distribution says. The normal distribution says 1 standard deviation to the right, or positive side, 1 standard deviation to the negative side. That area should be about 68% of your entire curve. Is that true here? Right? Is that true here? No, it's not. This does not look like more than 50% of the curve, right? This looks like, I don't know, maybe 1/3, right? Maybe a little less than 1/3, right? Now this is starting to look more like 68% of the curve, but still maybe not quite 68% of the curve. It still only looks like maybe 50% of the curve, maybe a little more, right? But this, oh, sorry, my picture is a little bit off, but this, imagine that this was shifted in the middle. This would be more like 68% of the curve, so let me draw it out here. So something like this would be more like 68% of the curve, right? And so, right? And so that's how you could see that as your degrees of freedom increases, it becomes more and more normal, right? Even this isn't quite normal. This isn't quite 68%. It's a little bit less, actually. But as the DF gets bigger and bigger and bigger, that area starts to look more and more like the normal distribution. Now, there is another way I could draw these pictures. And I believe in this other way, you could see more easily how this is sort of a more variable version. Remember, I'm saying the t distribution, it's like it's like you're stomping down on the peak of it, right, and smushing it out a little bit. And I believe that if I draw it in a slightly these same pictures in a slightly different way, you'll see why. So in this case, here's what I've done. I've kept the t axis the same, right? So now it's labeled in the same way. But I've drawn these distributions in a slightly different way. So now this one is a little like wider, this one is less wide, and this one is even less wide, right? So it becomes more narrow, more like the normal distribution, right? So notice that if I drew the line here, right? Here, a little bit after the 1, after 1 standard deviation away, we see very little of that curve on this side, right? So, you know, I don't know, if that's 50%, I don't know, maybe 15%, 10%, right? Something like that. Whereas this might look sort of more roughly equivalent to this, maybe a little bit less, right? So maybe like 20%, right? And then this looks like much more than this, right? So maybe this is like 25 or 30% even compared to this little sliver. And so in that way, you could see, using the same concepts, but drawing the picture in a slightly different way, that that this distribution is much more variable. Its spread is very, very wide, whereas this distribution is much less variable. And remember, T is all because of the variability found in S. When S is very, very variable, when n is very small, S is very, very variable, so the T distribution is also quite variable. As n gets bigger, S gets more and more accurate, more like this actual standard deviation of the population. And because of that, it becomes more and more normal. All right, so let's break this one down. So in degrees of freedom for degrees of freedom of 60, here's what it might look like. It might look something that's very close to our 34, 13.5%, 2% normal distribution, right? So if we drew our little lines there, right, that would probably look very close to sort of this picture, right? It looks pretty close. But when we draw something like this area might only be 25% of this whole curve, right? If that at all, right? And this other area is also combined 25%, right? And if I split this like this, then this would be something like 14%, right? So a little bit less than this, but still quite a bit, right? And so it looks, in fact, this one might even be more than 14%, maybe something like 18%, right? So you could see that in this distribution, it's going to, even though I've drawn it like this, and I've just labeled it differently, in reality, it'll look more like this if you kept this t-axis to be constant, right? It'll look sort of smooshed out. Okay.